Okay, hello everybody. Thank you for coming, and we'll go ahead and get started. It's my pleasure to introduce Waseem Bakr, who's here from the physics department at Princeton University, which you may have heard of. Waseem got his PhD from Harvard and was a postdoc at MIT before joining the faculty in Princeton in 2013. During his time as a graduate student in Marcus Greiner's group at Harvard, he helped build the world's first atom gas microscope and has continued to develop that technique and related techniques, applying it to fermionic atoms, to molecules, combining these kinds of techniques with Rydberg atoms and the like. His group has been at the forefront of studying quantum many-body physics in the form of ordered phases, Rydberg defects, and related topics. He's received numerous awards. These include Alfred P. Sloan Foundation, Packard grants, the AFOSR Young Investigator Prize, and the Brown Science Initiative Award, among others. And it's a pleasure to have him here today. So Waseem, welcome.
Thank you, Jack. Okay, it's a real pleasure to be here at Yale. It's my first visit. Let's see, already this is not working. Maybe I should stand there, click. We tested this before. Okay, so, there we go. Okay, so let me start with a broad overview of the kind of physics my group is interested in. So we're interested in understanding strongly interacting quantum systems that, of course, appear all over the place in condensed matter physics. So there you have systems where the electrons are interacting strongly with each other, or the spins are interacting strongly. And that can give rise to very interesting emergent phases of matter, give rise to new kinds of dynamics. And so here are examples of materials that have these strong correlations, things like high temperature superconductors, heavy fermions, fractional quantum Hall systems. And of course, many of the phases that appear in here might have very interesting technological applications. So we would be interested in trying to engineer the properties of these materials better. And for that, it's important to understand the microscopic physics of what's going on. But the challenge, of course, is that to do that, you have to solve the quantum many-body problem, which we know is very hard to solve in a classical computer beyond a few dozen particles. So the idea to get around this goes back to Richard Feynman in the 80s. What he suggested was maybe if you're trying to simulate a quantum system in chemistry or in materials, you shouldn't be using a classical computer, but rather let nature in a quantum mechanical system do the work for you. And that's the idea of a quantum simulator. So think of this as a very versatile and flexible quantum system, which you can use to program some sort of many-body Hamiltonian and then simulate the physics of the system of interest. So it's sort of like a quantum computer, but not completely universally programmable. It's suited to simulating certain classes of problems, whether it be in high energy physics or in condensed matter physics or chemistry. And people are trying to build these kinds of quantum simulators with all sorts of systems, from ions to photons to neutral atoms to superconducting qubits. So the focus of this talk is going to be how to make these quantum simulators with cold atoms. Here's a temperature scale. So this is here the temperature of this room, temperature of outer space, and we're all the way down here, about 9 to 12 orders of magnitude lower. So why do we have to be so cold? The reason is we want to study quantum mechanics, and we're working with these very dilute vapors. The typical spacing between the particles is on the order of a micron. So in order to enter into a quantum regime, you want the de Broglie, the thermal de Broglie wavelength to be large, to be comparable to the spacing. And for that, you have to cool down the systems to very low temperatures, because these atoms aren't like the electrons, they're much heavier. So you have to cool down to roughly the microkelvin to nanokelvin regime to start looking at quantum physics. Fortunately, we have in the AMO community a long history of cooling techniques, namely laser cooling and evaporative cooling. So here's a picture taken with a cell phone of a cloud of laser-cooled lithium atoms, probably what like Near and Charles have in their groups. So this is a blob of atoms that's a few millimeters across. You can see it with your bare eyes. It's carrying so many photons in the red, the resonance of lithium. And within a few milliseconds, you can cool this down with radiation pressure forces from the lasers down to temperatures of a few hundred microkelvin. If you want to get even colder to enter this quantum regime, you need to stop the scattering of the photons. So what you do is you can load the atoms into essentially a focused laser beam, very much like the tweezers people use in biology. You load them into this dipole trap, and then you can evaporatively cool them by spilling out the hot ones and letting the remaining ones thermalize. And you can, this way, get all the way down to quantum degeneracy. So if what happens next depends on the species you're using. So these atoms are like composite objects. If you have, for example, the species we're using here, it's lithium-6. It has 3 protons, 3 neutrons, 3 electrons. That's an odd number of particles, so that makes it a fermion. If you add 1 more neutron and work with lithium-7, you have a boson. So if you cool down lithium-6, you get a degenerate Fermi gas. You cool down lithium-7, you get a Bose-Einstein condensate. So this is starting to look like a good starting point for making something that looks like, the electrons in a solid. There you have a degenerate Fermi gas, even at room temperature. But if you want to make this look even more so like what you have in a solid, you might want to consider adding a band structure. After all, we know that band structures in solids are important for many of the interesting properties. And to do that, the tool we have is known as an optical lattice. So what you do is you take a bunch of laser beams and interfere them together to create standing waves of light, whether in 1 dimension, 2 dimensions, or 3, depending on the geometry. You can get whatever crystal structure you want. And you put the atoms in this crystal of light, and they can move around and acquire a band structure, much like the electrons in a solid. OK, so essentially what we've built at this point is an enlarged model for studying condensed matter physics. You've taken the length scales and blown them up by 4 orders of magnitude, because the spacings in a solid, are on the angstrom scale in the lattice. Here, the spacings are on the micron scale because they're set by the wavelength of light. And here, we're typically trapping with things like near infrared or visible light. So the relevant length scales are microns. The atoms are playing the role of the electrons in a solid. And so everything here is much slower. The distances they have to cover are larger. The atoms are much heavier than the electrons. So dynamics is really slow, typically on the millisecond scale rather than femtosecond. So it's very easy to study dynamics in these systems. And the beautiful thing about these systems compared to the solid state is that they really act as a quantum simulator in many ways. They have a very well understood microscopic Hamiltonian that we can write down, unlike in the solid state where usually whatever you use is a very crude approximation. Here, the Hamiltonian we write down is known with the precision of atomic physics. We can engineer it in many different ways. You can imagine, for example, tuning many of the parameters often in real time. You can control the lattice geometry. You can control, let's say you want to control the tunneling rate of the atoms between the lattice sites. You can just change the lattice depth by controlling the laser intensity. You can control interactions. So it's sort of like Lego blocks that you can build up to make whatever many-body Hamiltonian you're interested in. And for the purpose of this talk, the most important aspect of this system is that you can, because the length scales are so large, you can use this quantum gas microscopy technique that Jack mentioned to go and probe the atoms down at the smallest length scale. So essentially, you can take snapshots with optical light of this many-body system. So that would be like in a solid-state system looking at every single electron with just an optical photograph in this system. And at the same time, not only can you probe the system at this smallest length scale, but you can also manipulate it at this length scale. You can like shine laser beams and say flip the spin of this atom, or do other types of manipulations. So this is the sort of pictures we get. Of course, when you're doing microscopy on a length scale that's very comparable to like this wavelength of light, then you have to be diffraction limited. You want to work with a two-dimensional system, right? So you need to be really thin, these microscopy samples. So here we work with a 2D system. And when we prepare the system, we're starting from a well-understood quantum state. For example, a Bose-Einstein condensate or a degenerate Fermi gas. So these are, of course, simple textbook states, which we understand very well. But then if you want to get towards a more interesting state, you want to enhance the interactions. So one way would be to introduce an optical lattice, and that quenches the kinetic energy in the system and brings out the effect of the interactions. So if you ramp the lattice adiabatically, you're essentially transforming the Hamiltonian adiabatically, and you end up in some sort of correlated state that might be very interesting. So before taking these pictures, you can imagine the particles are delocalized in the lattice. They have this entanglement between them. And now when you want to understand the microscopics of the system, you take a snapshot with this fluorescence imaging. And essentially what you're doing is you're collapsing this many-body wave function onto a particular realization. Each atom just falls on a site. The spins are selected in your imaging basis. And now you can go and take many of these snapshots, one after the other. So you prepare the system over and over again under identical conditions. And you can take an expectation value of some observable in this quantum mechanical system of any sort of endpoint correlation function. So you could say measure the spin correlation function, or maybe some 3-point, 4-point correlation function, just the way that people in theory would calculate these types of things. So this is a very different set of tools from what you have in condensed matter physics. Of course, we can do a lot of the things that people do in condensed matter physics, like transport, measure things like spectroscopy, et cetera. But this gives us access to now the microscopics of what's going on. Okay, so I told you these quantum simulators are suited to certain classes of problems. They're not universal quantum computers. And so in my group, we have different types of platforms to tackle a broad set of problems. One of them is these fermions in optical lattices that I've shown you so far. Another is based on Rydberg atoms in optical tweezer arrays. And a third is based on replacing the atoms with molecules. And those molecules are polar molecules, and that allows you to access yet other sets of Hamiltonians. So broadly speaking, these types of things here allow us to study correlated electronic physics, relevant for things like high temperature superconductors or moire materials in condensed matter physics. These allow us to study spin models, and those allow us to study both spin models and various itinerant systems with long-range interactions. So that's sort of the set of Hamiltonians we can explore in the lab. Okay, so let me start. I'm going to tell you basically two stories, one about these Fermi gases and one about polar molecules. And feel free to interrupt at any time if you have questions. Okay, so I'll start with these Fermi-Hubbard models that describe correlated electronic systems. So these types of Hamiltonians were proposed shortly after the discovery of high TC superconductivity. Phil Anderson, Nobel laureate, who passed away recently at Princeton, he proposed that this might be a simple Hamiltonian to describe the essential physics of what goes on in a high TC superconductor. So it's a very simple Hamiltonian. What you should consider here is basically two species of fermions, like spin-ups and spin-downs. In our realization, those would be two different hyperfine states of the atom. You put them in a lattice. This could be of any geometry. For the first part of this talk, let's imagine a square lattice. And the fermions can do one of two things. So this first term allows them to hop between neighboring sites. And the second term is essentially a strong interaction on a site. So if you have a spin up and a spin down coming on the same site, they have a strong repulsive interaction. And it's the competition between these two terms that leads to a lot of interesting physics. So we have the ability to tune a lot of the parameters of this Hamiltonian. You can tune the interactions, the tunneling, the temperature of the system. When you put them on a lattice, there's an interesting quantity to look at, which is the filling of the lattice, the ratio of particles to sites. That controls a lot of the properties of the system. So we can tune all these things in the lab. And despite the deceptive simplicity of this type of Hamiltonian, it describes a lot of very interesting materials. People have been studying it for over 4 decades, and we still don't understand, even in the simple square lattice case, the low temperature physics of what's going on. Okay, so that got the cold atom community interested in trying to simulate these Hubbard Hamiltonians on a classical computer. The simulations become very difficult, especially when you go away from the regime of half filling, when you dope the systems. So we call a system undoped if you have an equal number of particles and sites on the average, but you can whole dope by taking some particles out, or particle dope by adding some extra particles. So that's where all the interesting physics happens in the cuprates. But that's also where classical simulations get really hard. So here's a cartoon phase diagram of what we have in the cuprates. We don't know what the phase diagram looks like in the Hubbard model, but hopefully it looks something like this. And these are just some of the key phases. There are many other rich phases here that are skipped. So this is in temperature and doping. In the cuprates, the electrons are interacting quite strongly. So if you go to the regime of half filling, or in an undoped system, where you have an average of 1 particle per site, you crank up the interactions, then you find that what the system wants to make is something called the Mott insulator, where you form 1 electron per site, because you want to suppress density fluctuations that cost interaction energy. Now, if you lower the temperature further, you get an antiferromagnet. So there's now spin ordering in the system. This comes from a process known as superexchange, where an electron hops over to a neighboring site and then hops back. You saw in the Hamiltonian, there's no direct interaction between particles in different sites, but you can have a second order process where you hop and hop back. So that goes as the tunneling squared over the interaction. And this leads to an effective spin-spin coupling on these different sites that's antiferromagnetic in nature and leads to this antiferromagnet. So these two phases, the Mott insulator and the antiferromagnet, are known to exist in the cuprates. They're known to exist in the Hubbard model, where we can do simulations quite accurately with a technique known as quantum Monte Carlo at half filling. So they're basically good phases to benchmark our quantum simulator on. But then if you dope the system away from half filling, quantum Monte Carlo starts to run into problems. There's something called the fermion sign problem. So it's hard to predict things at low temperatures. But that's where all the rich physics in the cuprates is. So for example, you have this famous D-wave superconductor down here. But even in the normal phase, like here and here, there's very rich physics. This is called the strange metal, where you have unusual transport properties. Here you have a pseudo-gap regime, where you have unusual spectral properties. So these are some of the things where the quantum simulators might shed light on the microscopics. Okay, so I want to quickly review some of the key physics that these microscopes have revealed about these Fermi-Hubbard systems on the square lattice in the past 5 years or so. Or past more, 10 years. This is a picture here from the group of Marcus Greiner at Harvard, where they crank up the interactions in a half-filled system, and you can see microscopically this Mott insulator. Just you can see it from the pictures. You see 1 atom per site. Okay, occasional defects that have to do with the imaging. You can also see the antiferromagnetic phase, which is another of these phases I mentioned at half filling. So here, what you have to imagine is this system at half filling at strong interactions. It has this 1 atom per site. that are coupled through the super exchange. And it turns out the effective description is a Heisenberg model, a Heisenberg spin model. So this is a quantum antiferromagnet with a lot of quantum fluctuations in it. So if you take the snapshots, you're going to have a hard time seeing the antiferromagnetism, but you can take these snapshots over and over and take an expectation value of the 2-point spin-spin correlation function. And lo and behold, you get clear checkerboard order emerge. So this is here the spin correlation function extracted from the snapshots. So this can all be quantitatively compared to results from quantum Monte Carlo, where I said at half filling, things can be calculated very accurately. And there's very good quantitative agreement. You usually have to leave the temperature as a fit parameter. So that allows us to actually extract blue thermometry on these systems by fitting to the data from quantum Monte Carlo. And this gives us an idea of the temperature of the systems. It's typically, we can get to temperatures in the best case, about 15% of the tunneling energy scale. So in that regime, if you start to dope, that's outside of what quantum Monte Carlo can do at that point. Typically, there you stop at about 30% or so. So this is already, if you want to think of this as a quantum simulator, it's in a regime of quantum advantage. Okay, so indeed, I told you that the interesting part is once you dope. So here are some key results from these doped square lattice Hubbard systems. This is work from my group where we tried to go to this part of the phase diagram here, the strange metal. So in the cuprates, what's observed is that there is a regime in the normal phase where there is a linear resistivity in temperature. If you vary the temperature of the system and map out the resistivity, it scales linearly. And this is very unusual because in a system where the interactions between the electrons are the cause of the resistivity, Fermi liquid theory would predict that you should get a quadratic scaling of the resistivity with temperature. So, however, in the cuprates and many other correlated materials like bilayer graphene and so on, you observe this unusual behavior where the resistivity is linear, and that's something people still don't understand. And there was a question of whether the Hubbard model can actually produce this type of behavior. And indeed, we did these experiments in my group, and we found that indeed the resistivity is linear in temperature. So at the time, nobody had done the numerics on this, but shortly after we did the experiment, various groups started pushing these numerical techniques and running them for super long times, and indeed, they could reproduce these results. So this is, for example, an example of an exact technique. You can have this is here finite temperature Lanczos. You use quantum Monte Carlo. These are exact techniques, and they indeed reproduce this linear in temperature resistivity. Other techniques, like here's a commonly used technique in condensed matter physics. This is dynamical mean field theory. This is a very commonly used technique, but you can see it shows very large deviations from the data. And so you can see here the value of these quantum simulators in being able to distinguish between different theories and tell you what theories are good, what theories need to be supplemented. So for example, here, if you add so-called vertex corrections to this theory, then the agreement is much better. So it's starting to guide the development of these various theoretical techniques.
Yeah. Pausing for the folks on Zoom. Let me.
Yeah.
Maybe I missed something, but are you saying that you're measuring resistivity?
So in this experiment, we don't measure the resistivity directly. We kind of go around it in a roundabout way. We use the Nernst-Einstein relationship. So we measure the diffusivity actually, and then we measure the compressibility and multiply them to get the conductivity, take the inverse to get the resistivity.
Okay.
Yes. Okay, so this is bulk transport. This is the kind of thing you could do in condensed matter physics. Falling down a little bit. Okay, but the advantage of these microscopes is you could also do microscopics. And these are experiments from Marcus Greiner's group at Harvard and from Emanuel Bloch's group in Munich, where they actually start from an antiferromagnet at half filling and inject a hole into it. And then they can go microscopically track what the hole is doing in the system. So this is basically a microscopic version of these experiments, essentially in the limit of zero doping, just one hole doping. And a lot of the interesting physics of the cuprates has to do with the interplay of spin and charge degrees of freedom. And so here the physics that was studied was you can look at the transport of the hole in the antiferromagnet. As you can imagine, as the hole moves around, it disturbs the antiferromagnet. And so what you could do microscopically is you can find a dopant in these snapshots that you introduced, and then evaluate the spin correlations around it. And you can look at the local disturbance of the spin correlations around a hole dopant, for example. And so that's basically a quasi-particle that emerges in the system due to these mobile holes that are addressed by these spin fluctuations or correlations. This is what's called a magnetic polaron. And here you can directly visualize these things. You can just take a picture of the polarons. So these are things that were there in textbooks for a long time, but here, for the first time, you can actually just go and visualize it in a condensed matter, in a many-body system. Okay, so that's a quick review of what people have done in the past. Now, I want to tell you about some more recent work we've done on Hubbard systems in a triangular lattice. So this is a different lattice geometry, and probably many of you know the interesting thing about the triangular lattice is the frustration. So actually, this is a problem that Phil Anderson had studied even before looking at the square lattice Hubbard model. So he was actually looking at a triangular lattice and studying the Heisenberg model on it. Remember, the Heisenberg model is the limit of the Hubbard model in the regime of strong interactions at half filling. And so if you put antiferromagnetically coupled spins on the triangular lattice, the key thing that happens is, of course, you can put the first spin, let's say up, the second spin you want to point down, but then you're not sure what to do with the third spin, right? So this is the phenomenon of spin frustration. And Phil's idea to find a ground state in this Heisenberg model was maybe what you want to do is to pair up these spins in a spin singlet and then cover the entire lattice with these singlets. But there's no reason to pick a particular covering, so maybe what you want to do is create a superposition of all these coverings. And that's what he called a resonating valence bond state. So this was the beginning of the field of quantum spin liquids, which is now a very exciting area of condensed matter physics. Like many of the things that Phil started, this was exciting, but it was actually not quite right. So in this case, it turns out that actually the system finds a way to order the spins in this triangular lattice, and that's by arranging the spins in the plane at 120-degree order relative to each other. So that's what's called sometimes a spiral antiferromagnet. Interestingly, more recent work on the Hubbard model, which is now taking this Heisenberg model, but allowing for charge fluctuations, there, people are still studying that, but it seems very likely that in the regime of intermediate interactions, there might be a quantum spin liquid in the Hubbard model. Okay, so the point here is that you can see there's already very interesting physics, even at half filling in the triangular lattice Hubbard model. And things will only get more interesting if you start to dope. So that spurred my group and a couple of other groups to start using microscopy on these triangular lattices. And so now we're looking at a Hubbard system on a triangular lattice, and we can get basically snapshots of the spin ups and the spin downs simultaneously. So we can reconstruct the full information of this Hubbard system on the lattice site. You can tell whether you have a spin up on a site, a spin down, a hole, or an up and a down, which are all the possible configurations you can have on a site. Okay, so we take these snapshots, and now we can extract, for example, the 2-point spin correlation function. So here's the data. You can see it here. And yeah, so actually, this is something I'm skipping over. So actually, here what we do is we make a square lattice, but we connect, we allow tunneling along the diagonal. We can control things a bit better, and we can allow tunneling along the diagonal. So this looks like a triangular lattice, an isotropic triangular lattice. Okay. But the row images are square, you're right. Okay, so we look at the 2-point spin correlation function, And here, again, it's a quantum antiferromagnet. It's a very complicated state. When you look at the correlations functions, you get this data. I've overlaid on top of that the classical triangular spiral antiferromagnet, which you get in the regime of strong interactions. And you can see that indeed what we measure is consistent with that. So if you fix this central spin and you look at this spin here, in the spiral pattern, this would be primarily anti-aligned. So that's a negative correlation. While here, they're primarily aligned, and that's a positive correlation. And the finite range of the correlations here is due to the finite temperature of the system. Okay. Okay, so that's basically looking at some of this spin physics in this large U limit where you have the Heisenberg description. So this was kind of relatively well understood physics, but the more interesting physics, in my opinion, is once you start to dope. And here there were simultaneous experiments that were happening in the condensed matter community. So for the condensed matter people here, probably a lot of you are familiar with these moire systems, which are one of the hottest fields right now in condensed matter physics. You can take these 2D materials. An example here is these transition metal dichalcogenides. You can stack them on top of each other and twist them relative to each other. And you get effective moire lattices. And in these materials, you can get, for example, a triangular lattice where the interactions are very strong due to the presence of a flat band. And so you get this sort of effectively like a triangular Hubbard model with large interactions. So pretty much the same system where I've been describing with cold atoms. You can get a reasonably clean realization in these materials. And so one of the experiments that caught our attention is these experiments from the group of Atachi Mamoglu at ETH and from the Kim-Fai Mike group at Cornell. So what they were doing in these experiments were they were starting from a triangular lattice, and then they were doping the system with a gate, and so they can go from particle doped to hole doped. And they were measuring the spin susceptibility in the system. And what they observed was if they hole dope the system, you get an antiferromagnet. While when you particle dope it, you get a ferromagnet. So this is a susceptibility, the spin susceptibility depends on doping. So very interesting maybe from a technological point of view. And the other interesting thing was this magnets were appearing at quite high temperatures compared to the expected super exchange in the system. Okay. So Eugene Dembler, our theory collaborator, was working with these guys, and he had a microscopic theory of what's going on. And he told us maybe you guys could go test it in your quantum simulator. So I want to explain how this new type of magnetism, this new form of magnetism emerges in these triangular lattices that is very different from the type of magnetism that we're used to in square lattices. So this is what's called kinetic magnetism. And the key aspect of the story is a different kind of frustration that appears in triangular lattices is called kinetic frustration. So it's different from the spin frustration you might be used to. And to explain that, let me start from a very simple setting. Let's just imagine a triangular lattice where you put a single particle on it. So you know what the ground state is. You just want to delocalize the particle over the lattice. If you just have a single particle, there's no interactions, you have a very simple Hamiltonian where all you have is just a tunneling. Then you know that the band structure looks something like this. And if you want to put the particle in the zero quasi-momentum state, so you lower its energy by the number of nearest neighbors times the tunneling. Okay. All right, so maybe a more contrived way of describing this would be to say, what I want to do is maybe delocalize the particle over this bond. So I create a symmetric spatial superposition on this double well. And then I delocalize it on the next bond and the next bond. And I can do this because all the phases are the same in the system. So I create a symmetric superposition of all the sites. Okay, so let's now consider the opposite situation. What if I start from a spin polarized system? So all the spins are pointing up. And now let me introduce, instead of a particle, a single hole into the system. What changes? Well, it's still a non-interacting system. So all I have is the tunneling. And I'm going to introduce a single hole into the system. So maybe it makes sense to rewrite this Hamiltonian in terms of hole operators. So you create a hole on a site by destroying the fermion. Well, if I do this, the C dagger C here will switch to H dagger. But remember, this is a fermionic system, so I need to keep track of the order of the operators. You want them to be normal ordered. So what you want to do is to anti-commute those two operators to recover the usual order. But since they're fermionic operators, you flip the sign, right? So you get a plus sign here. So the sign of the tunneling has just switched, right? So basically the band structure flips around. And now what you want to do is put the holes over here rather than here. Okay, so you minimize the energy in the flip band structure by sitting here. So you see, you don't lower the energy as much as you did for the particle. Another way of saying this is you now imagine, again, the story on considering what happens on bonds. So if you delocalize the hole over here, you want to now create the anti-symmetric orbital, right? Instead of the symmetric one, because you flip the sign of the tunneling. And then you can repeat it on the next bond. That works out, but it doesn't work on the third bond of the plaquette, right? So there's a frustration very much like what you had with spins, but now in the spatial degree of freedom. So that's what's called kinetic frustration, okay? And basically the hole is unhappy. It can't move around as much as a particle because of this kinetic frustration. And you can trace the reason for this to destructive interference. So as the hole moves around in the spin polarized background, the different pathways it takes through the different bonds of the plaquette will destructively interfere. And so the hole kind of gets less mobile and gets stuck. So how do you get rid of this frustration? Well, you know what to do to remove interference is you want to introduce some which way information, right? So you want to introduce some distinguishability in the system. And one way to do that would be to flip some spins in the vicinity of the hole. So then if the hole goes this way, it shuffles the spins one way. If it goes the other way, it shuffles them another way. And then you remove this destructive interference and the hole gets freed up. Okay, so now it's more mobile again. So it seems around these hole dopants, what you really want is not aligned spins, but anti-aligned spins. So you see the hole mediates antiferromagnetism. And this is nothing to do with superexchange. I could be working at very large interactions where the superexchange vanishes. Just the motion of the hole mediates this antiferromagnetism in the system. Okay? So the energy scale for this is not the superexchange scale T squared over U, but a much higher energy scale, which is the tunneling energy scale. So this is high temperature magnetism. Okay? So that's the key idea is you want to form these quasi-particles in the system where around the hole dopant, you want anti-aligned spins. So the building block of this antiferromagnetism is this type of object where you have a hole dopant with two anti-aligned spins around it. That's the polaron that emerges in this system. And its binding energy is on the order of the tunneling. There were a lot of predictions of the existence of this polaron, inspired a lot by what's happening in the Moiré community. But of course, in the Moiré community, they don't have this ability to go and look at microscopics. In our case, we do. So indeed, what we did was go and prepare a triangular Hubbard model, and then introduce some dopants onto the Mott insulator, and take snapshots, find the dopants, and now look at the spin correlation around the dopant. So here you see the expectation value of these spin correlations experimentally measured. And what you find is indeed around a hole dopant, the sign of the bonds is antiferromagnetic. So locally you form antiferromagnetism, a bubble of antiferromagnetism. And if you look further out, it starts to look like an antiferromagnet. Okay. Interestingly, if you flip the sign of the doping from holes to particles, all the story I told you about with the first kinetic frustration goes away. And here what you want to create instead is ferromagnetism, just like they saw in the Moiré experiments. So we find that as you reduce the doping from the particle side closer and closer to the limit of a single dopant, we find a bubble of growing ferromagnetism in the system. So that's these red bonds here. And this is, for the experts here, maybe you know about Nagaoka ferromagnetism that was predicted like decades ago. It was a rigorous mathematical theorem proved by Nagaoka and seminal work, but it was under very strict conditions. You had to take the interactions to infinity, a single dopant, conditions that nobody saw in a real system. So this was never observed in a real system. But once you put it on triangular lattice, it seems all these conditions are relaxed. And now you can observe this ferromagnetism in these systems. Okay, so there's a lot of interesting extensions of this work. You can now look at more complex polarons. Turns out there are polarons where you bind multiple spin flips and multiple holes together, and the energy scale is still the tunneling. So you can think of this as a mechanism for binding holes, which can then condense and give you a superconductor. So this could be eventually a mechanism for high TC superconductivity of a completely different type than what you have in the square lattice. Okay, so now I want to switch gears to a different platform in my group. And now the motivation for switching from atoms to molecules is that we want to introduce long-range interactions. So far I've been telling you about these Hubbard systems where the interactions are purely on-site. And the reason for that is that between ground state atoms, the interactions are these short-range van der Waals. So atoms on different sites in an optical lattice don't see each other almost at all. But if you switch to molecules with a dipole moment, those can see each other at long range because of the 1/r³ dipolar coupling. And so we can engineer a new set of Hamiltonians with these systems. And these molecules not only have this long-range interaction, they also have new degrees of freedom, right? Compared to an atom, which all it can do is translate. Here you can have, even in the simplest case of a diatomic molecule, you can have vibrations, rotations, and so on. And you can encode information in these new degrees of freedom. And some of these degrees of freedom are very long-lived. So people have shown that you can get second-scale coherences of things like rotational states. So if you prepare a superposition of rotational states or a superposition of hyperfine states, the coherence times are on the second scale. And this is to be compared to the dipolar interaction strength when you put these on neighboring sites of a lattice. That's typically milliseconds. So you have, if you think of this as a quantum computer, you can do maybe about 1,000 gates before the system decoheres. Okay, so in the context of many-body physics, these molecules offer a lot of possibilities. If you're thinking about the Hubbard-type systems I described earlier, now you have this long-range interaction. So you can realize what's known as extended Hubbard models, which can lead to a whole new rich set of phases, like these quantum solids is one example. If you let them tunnel around in a Hubbard system. But even if you freeze them on sites, they still couple because of these dipolar couplings. And there, the interesting physics would be to open up the rotational degree of freedom. So let's imagine you prepare the molecules in the state where they're not rotating. Okay, you prepare them in one defined rotational state. And now you couple them to another state where they're rotating with 1 unit of angular momentum. So that could be a spin 1/2 or a qubit. And now they're coupled to each other with these dipolar couplings. And so that's basically a way to engineer a wide variety of quantum spin models. And I'll show you examples of that shortly. So the challenge with molecules compared to atoms is they're much harder to get cooled into this quantum regime. And actually, a lot of the pioneering work in cooling molecules happened here at Yale when Dave DeMille was here. So usually with these molecules, you don't have cycling transitions where you can use a laser beam to cycle in a particular transition and slow the molecules down because they would just fall into other rotational or vibrational states once you scatter some photons. But Dave and others identified certain classes of molecules which are amenable to laser cooling, and that's one approach that people are using. So far, people have loaded those into optical tweezers and made small systems of a few molecules in these arrays. The advantage of this approach is you can see the individual molecules, you can scatter photons of them, and they're not very cold. They're still within the tweezer, they're occupying many motional states. The complementary approach that was pioneered at Gila was to say, throw up your hands and say, I don't know how to cool molecules, but I know how to cool atoms. So maybe what you want to do is to just produce 2 degenerate gases of atoms, and then you can bind them together into a molecule by sucking out the binding energy with a photon coherently. And you form these ultra-cold molecules. So the advantage is we know how to produce very emotionally cold atoms. We can produce degenerate gases. So the molecules produced this way can be quantum degenerate. So people have produced degenerate Fermi gases and Bose gases of molecules this way. And the numbers here are much larger. Here we're talking about tens of thousands of molecules compared to the few that people have produced this way. Okay, so we're greedy in my group, and we decided we want the best of both worlds. We want the single molecule control, where you see individual molecules and control them, but work with a large number of molecules which are also motionally cold and allow you to do things like Hubbard physics and so on. So what we decided was to combine this assembly approach pioneered at Gilla with the microscopy we know how to do for atoms to create what's so far the only molecule microscope in the world. Okay, so this is a microscope that can see the individual molecules in the lattice. And so the molecule we're using in my group is sodium rubidium. Sodium and rubidium are both bosonic atoms. So if you bind them, you'll get a bosonic molecule. And if you cool it down to the ground state, you'll get a Bose-Einstein condensate. So here you can't study Fermi-Hubbard physics. You would more look at Bose-Hubbard physics. But there are other molecules you could use to study Fermi-Hubbard physics. We produced this following the footsteps of Junyi and Debbie Jin and Kangwen Ni at Gilla. So what we do is we first bind these molecules into a very weakly bound fragile molecule known as a Feshbach molecule by using a magnetic Feshbach resonance. And then we can, this is a large fluffy molecule which the atoms are so far away that they don't polarize each other. You don't get a dipole moment. So you can bind them into a much more tightly bound molecule by sucking out the binding energy with a 2-photon process and transferring them to the absolute ground state. So this is basically a molecule that's not rotating, not vibrating. It's in the ground hyperfine state, ground electronic state. So all the quantum numbers are very well defined for this molecule. So this is a molecule where you can start thinking about doing quantum science. Okay, so in the last 5 minutes, I'll show you some science we've done with this. So here's a bit more about how we produce these molecules. So we simply start with BECs of rubidium and sodium. We load them into an optical lattice. Occasionally, one atom of rubidium and one atom of sodium land on the same site. If that's the case, we can convert them with 100% efficiency into a Feshbach molecule. We can verify it's a molecule by measuring its binding energy, which at this point for Feshbach molecules, it's very small. It's kind of on the tens of megahertz scale, as opposed to like hundreds of terahertz you have in a real molecule. Now we want to image these molecules. I said here you've produced molecules in a fraction of the sites, but there are other sites which just still have atoms which we can blow away. So we don't know which sites produce the molecules. So to figure out which sites produce the molecules, we want to do microscopy. And I said this is hard for our molecule because we don't have these cycling transitions. But what we can do is we can just reverse this entire process. We can take the molecules back to atoms and look at, say, just the rubidium atoms in the molecule. So the rubidium atoms would act as a tag that tell us where the molecules are in the system. So these are the kinds of pictures we get. These tell us, here are your molecules on these sites. I'll show you later, we can also know what internal state the molecules are in. So here they're produced in a well-defined internal state, but later we can produce superpositions of these states. Okay, so now I want to study some quantum magnetism with them. So we have to transfer them down to the ground state. We can do this with a pretty high efficiency. And the trick here is to study quantum magnetism is to indeed use these superpositions of rotational states as I described. So here's an example from Gilla where they produced the molecules in the ground rotational state, which we might call spin down. And then you can, this is like a rigid rotor spectrum for the molecule. So you can use microwaves to couple to an excited rotational state. So one of them, let's say a molecule that's rotating like this. Okay, so those are your two spin states, your spin up and spin down. Now they're coupled through a dipolar interaction, and what that does is it allows you to exchange rotational excitations between the molecules. So like this one might be rotating, this one is fixed. Then the dipole interaction allows this to rotate and this one to be fixed. So in terms of a spin model, what that looks like is a spin exchange model. You're exchanging this rotational excitation. So in condensed matter physics, this is what you would call an XY model. Okay, this is a quantum XY model because the spins are quantum mechanical. And the coefficient here is a dipolar coupling. So it has the usual angular dependence and 1/r³ dependence of dipoles. And so in this pioneering experiment from Gilla, they didn't have a microscope. They could prepare this bulk system. They can prepare, say, a superposition of up and down. So maybe you prepare like the state that's pointing along the X. So that state is not a ground state of the XY model. It's a ground state of the classical XY model, but in the quantum model, there's all these quantum fluctuations that can happen. So this is kind of a state that's out of equilibrium. And so you expect it to start thermalizing and you go to eventually to some unpolarized state. And they could track the polarization as a function of time by measuring this polarization. And they can see some oscillations that have to do with the nearest neighbor interactions between the dipoles. So we decided to repeat this experiment with our microscope, now tracking the spreading of correlations in this non-equilibrium system. We want to see how the correlations spread as the system thermalizes. So I'll show you some of the key ingredients here. So here's the rigid rotor. We can isolate two states and drive very nice Rabi oscillations between them. So it's a good spin 1/2 or a good qubit. Of course, for a good qubit, you not only want this, but you also want to have good coherence between the spin states, right? And for that, the standard atomic physics technique is a Ramsey experiment. So you can prepare the spins like this and let them evolve for some time and read them out with another pi/2 pulse. And there are various sources of decoherence in the system that have to do with the fact that we're putting the molecules in some trapping light that has different effects on the different spin states. You have magnetic fields, electric fields that can couple to the molecules. So these are external sources of decoherence. And internally, the spins are interacting with each other, right? So that's, if you wish, you might call it the decoherence, but it's really a closed system dynamics. And what we find is we have coherence times that are several hundreds of milliseconds, and they're actually in agreement even for our very dilute samples where we try to reduce the interaction effects. They're still consistent with interaction effects. So it's really closed system dynamics that we're realizing here. Okay. So we increase the filling in the system, and now we could look at things like this quantum XY model. We can look at the spreading of correlations in the system and how they evolve with this microscopy. So one of the interesting things we've seen here in this spreading of the correlations is you could look at the correlations as a function of the separation of the sites in the system. And you see these very nice oscillations. So this is a relatively dilute system, about 5% filling. So you can imagine you have little puddles of molecules here and there. So sometimes you get like an isolated molecule which doesn't have any interesting dynamics. But then you have like maybe a pair of molecules. And if you're dilute enough, that's the dominant configurations you have in the system. So if you have a pair of molecules, they're exchanging this rotational excitation between them, you expect some very nice oscillations to appear in the system. And that's happening at the frequency of the dipolar interaction between these two molecules. So if you look at, say, two sites that are neighboring versus on the diagonal versus further apart, you expect to map out the 1/r³ interaction dependence of the dipolar interaction. The decoherence you see here is actually, again, not external. You can reproduce it through simulating the system. This is due to the long-range interactions in these, because it's ultimately the 1/r³ couples all these puddles to each other. Okay, so I want to maybe close here by just show you a little bit more about the tunability of these systems in terms of studying quantum magnetism. So I've shown you the simplest type of Hamiltonian you can realize, the quantum spin exchange model. This is in the case where we fix the quantization axis set by a magnetic field orthogonal to our 2D plane. But you can imagine if you tilt the dipoles, if you tilt the quantization axis into the plane, then you can have the dipole interaction act differently in the different directions, which can cause things like frustration and so on. So in terms of studying ground states, that would be a very rich area to look at. And we can verify that we can do this by, say, looking at the spreading of correlations with this tilted axis. And there you can see here, this was the isotropic case. This here, you can see much clearer anisotropy in the spreading of the correlations. So this is tuning the spatial anisotropy of these Hamiltonians. But another thing is you could go completely outside of the spin exchange model. So we've engineered more arbitrary XYZ models, so anisotropic Heisenberg models. So you can do that by Floquet engineering. So you can imagine, for example, letting your molecules evolve for a little bit under the XY Hamiltonian, but then rotating the Bloch sphere with a microwave pulse. So now what used to be XY becomes XZ, for example. And if you do this fast enough, back and forth, then the average Hamiltonian is an average of the XY and XZ, and you get something like an XY, XXZ model. Turns out if you control the timings, you can get any XYZ model, a large set of XYZ models that you might be interested in looking at. We've verified the correlations agree. So to summarize, we've really now taken this molecule platform to the point where it becomes a very rich quantum simulator of spin physics. We can do microscopy to look at the individual molecules. You can engineer all these different spin Hamiltonians, and the coherence times are extremely long compared to the microscopic interaction time scale. So of course, we'd love to next start letting these molecules roam around in the lattice and then connect to the Hubbard physics that I described in the first part of this talk. So with that, I want to thank the people that did this work. On the molecule experiment, most of the work was done by Jason Rosenberg and Lysander Christakis, who was actually here at Yale, and he worked with one of the faculty here. And the Fermi-Hubbard physics that I talked about was mostly the work of Max Pritchard and Zheng Liba. And thank you very much.
Okay, so thank you to Waseem for the talk. We have time for some questions. As is the practice, I will pass the microphone to whoever has questions. I can start. So you told this very nice story about kinematic frustration on the triangular lattice and how the Hamiltonian for a hole moving around sort of looks like the Hamiltonian for the electrons, but with the minus sign. So is it possible to go back to that? Is there, I think if I sort of track what happens if I move the hole around the triangle and sort of picture it as that, 15, 16 puzzle, I think I end up swapping the two electrons that are on the sites.
Swap the two spins.
Yeah, and is that sort of where this minus sign is coming from?
Well, okay, so I said there's a minus sign that comes from anti-commuting these operators. So here, this example that I gave you was for a spin polarized gas with a single hole in it. And when you write it in terms of hole operators, you want to always kind of normal order the operators. And then you flip them and you get this minus sign. But indeed, there's another minus sign that you bring up, which is the one that cures the frustration. So I might have that in a slide, actually. There we go. So, this is all happening in the regime of large interactions. So you can imagine if you work on a plaquette, the limit that's interesting to study is to put a single hole with two particles. That's like hole doping. You start with 3 particles, you introduce 1 hole, right? So then you'll get 1 particle on each site. And so that now, since you're going to large interactions, they're effectively looking like spins. And you can think in the Hubbard Hamiltonian it turns out the spin commutes, and so you can talk about the triplet sector and the singlet sector of the spin. And in the triplet sector, things are pretty boring. If you take this hole and you tunnel around, you go around and you exchange the 2 spins and nothing interesting happens. But indeed, like you point out, in the singlet sector, you swap the 2 spins. Oops, not shown here, but you can imagine they swap, and then you get a minus sign from flipping the 2 spins in the singlet if you go around once. And so that minus sign, which you get by flipping the spin, is exactly what cures the frustration. And you get essentially what's known as a spin Barry phase. that releases an amount of energy of order T and allows the formation of this polaron in the system.
Okay, thank you. Other questions for Waseem? Peter?
So I think you've been verifying the systems that you have with digital simulations as well. May I ask what the compute complexity and costs are for those simulations currently?
So for the Hubbard stuff, a lot of the work was done with quantum Monte Carlo. I don't know if I have I mean, I'm sure it's a polynomial scaling at half filling, but when you dope the system, you run into this fermion sign problem, and then basically what you see is that as you lower the temperature of the system, the sign fluctuates wildly, and like it gets really hard to simulate below about 30% doping. So the state of the art in the simulation is now like 15%. So you can only simulate the half-filled part, but not the doped part. And then there's other experiments like dynamics where things are just horrible, like if we're doing transport measurements, or like right now we're doing, for example, an experiment where we're doing spectroscopy on these polarons. So that involves computing a spectral function if you want to compare to theory. And we just can't do this on a Hubbard system anymore. So there you have to start using things like mean field theory and so on. And there's no guarantee that these things agree. For the molecule stuff I described, there what helps us a lot is that most of the system is in these small puddles. So you can kind of do an expansion in the size of the puddle, and like you can reproduce things there quite well.
So do you feel that you have a good control over the Hamiltonians of the system and a good understanding of that, so that as you scale beyond the point where you can do any digital simulation, you'll feel confident that you will be able to simulate other systems?
I mean, this is part of the problem of this kind of what people call the NISQ era, is that we have to trust that. I mean, we can test the Hamiltonian in certain regimes, like this half-filling regime or higher temperatures. But then as you go and measure in other regimes, all you have is these approximate theoretical techniques to compare to. And yeah, it's kind of hard to know whether what you're doing is correct or not. Of course, now there's people are working on these universal quantum computers made of logical qubits. And there you have this error correction that can help flag errors and so on. But the problem is, these computers are still like, there was a few simulations, I think, of spin systems and logical qubits, but they're very far from trying to do like a Hubbard system, like electronic simulations. That's the overhead you need is insane. So I think those are still, these analog quantum simulators, I think, are safe probably for 10 years or so, but hopefully I don't turn, well, hopefully or unhopefully I turn out to be wrong.
Okay, maybe time for one last question. Okay, Edward.
Hi, I was interested in your extended Hubbard model.
Yeah.
So I saw some plots there where the interaction was non-monotonic and in fact negative.
Yeah.
At some point.
This one here, like.
No, maybe a plot before, but well, yeah, I think that represents the same thing.
Yeah, this is here the interaction.
Yeah.
Sort of direction.
So if I was to think about this from my solid state background, I would think that if you have a minimum there, you'd be susceptible to some instability in the charge sector, like a charge density wave or maybe superconductivity. Is that realizable?
Maybe this is what is shown in this cartoon here. There's these quantum solids that form. So those are like, you can think of them like fractional Mott insulators that can appear because of this long range interaction. So people have seen this actually recently with magnetic atoms, still not with molecules, but.
And then their spacing will be corresponding to where the minimum in that interaction is, or related to that.
I mean, I think this is kind of the limit of, some sort of this instability eventually causing this.
Okay.
Okay, so with that, let's thank Waseem one more time.